Dear professors, good afternoon to everyone. On behalf of Department of Aeronautical Engineering, I hereby welcome Dr. Indrani Sen, Associate Professor of Department of Metallurgical and Materials Engineering, IIT Kharagpur. We welcome you, ma'am.
Thank you very much, Professor.
It is our immense pleasure and honor to introduce you, our distinguished resource person, Dr. Indrani Sen. She is currently working as Associate Professor in Department of Metallurgical and Materials Engineering at IIT Kharagpur. She did her Alexander von Humboldt postdoctoral fellow at Chemnitz Technical University, Germany. She completed her doctorate at Indian Institute of Science, Bengaluru. She did her master's in Materials Science and Engineering from Indian Institute of Technology, Kharagpur, by securing a silver medal in her academics. Her research area mainly focuses on shape memory alloys and smart materials, improved structural materials, additive and laser-based manufacturing, marine structural engineering, advanced alloys and superalloys. We are very much happy to have such an eminent personality here for our faculty development program. Once again, we welcome you, ma'am. Over to the speaker.
Okay, thank you very much, Professor, for this nice introduction and letting me talk on a topic which is very much dear to me. So I'm happy to see that there are many participants for this program, and I must also congratulate you for holding up such a FDP with such an interesting topic, which is kind of the state of the art for the present scenario. Okay, so let me then share my presentation and okay. Now I need to check on one option which allows me to share the sound also while I'm sharing the content. Is my screen visible now?
Yes, ma'am.
In the full screen mode?
Yes, ma'am.
Okay, great. Okay, so before I begin, let me just ask you that I can see many of the participants, but what are the usual background of the participants? Are you aerospace engineers or mechanical engineers, or is there anyone with materials or metallurgy background? This will help me formulate.
Yes, ma'am. Actually, we have participants from mixed background, that is from aerospace, material science, mechanical engineering, mostly.
Okay, mostly mechanical engineering. Okay, fine. So I will try to cover the very basic parts so that it should be understandable to everyone. But if at some point you are, if at any point you find that this is confusing or you are having any doubt, you can ask me questions, whatever you feel like. Okay, so the title is a little bit more than just the shape memory alloy. It is a microstructure and property correlation of nickel titanium based shape memory alloy. Okay, so before I start, let me give a brief overview of where I come from. So this place is here at the eastern part of this country, and this is the first ever IIT made in our country. Established in 1951 by the then and the first Prime Minister of India, Pandit Jawaharlal Nehru. So we still have the old building here. So this is the old building with the IIT inscripted on this, and this is actually in the land of Hijli, where we had the Hijli detention camp for the freedom fighters. So there are jails inside the campus, and this jail and this as well as this building itself is now a part of the museum. And we take really a very good pride in converting a land of such great personalities into a land of knowledge. This is our present building. Many of you might have seen this or visited this. So on the basis of this model, this is the main academic building of our institute. And this is my group, very recently taken, where one of my student has graduated, and actually he is joining as an assistant professor at IIT BHU today itself. So I thought of just sharing the picture of my group. This is my group logo. We mostly work on microstructure and mechanical properties. So in a very broader way, it can be termed as microstructure mechanical property correlations group, and we work on both the conventionally processed as well as additively manufactured materials. And not only that, we do the studies at all length scale. By that I mean that at the macro scale, we do study the quasi-static, tensile, compression, fracture, fatigue, all different kinds of fatigue behavior of material. And in the micro and nano scale, we do nano indentation very extensively and get to do some small scale mechanical testing also. Other than that, since we work on shape memory alloy, and one of the niche application area of this material is as biomaterial, we also study the in vitro mechanical behavior of this material as well as other materials as well. So what we do is we study the tensile and fatigue properties of this material while the specimen is immersed in a body-like, human body-like environment. This is also important when we are talking about marine applications. So we need to figure out what would be the performance when it is in a saline atmosphere. We also try to find out the high temperature properties, tensile and fatigue properties, and this is particularly relevant for titanium-based alloys which are used for aerospace application. We do work on different kind of material. Major work is going on the nickel titanium. Other than that, we also have research activities focusing on different categories of titanium alloys. And then, of course, stainless steel forms the main backbone of metallurgy. So we also do work on several grades of stainless steel, both conventionally processed and additively manufactured, as well as different categories of nickel-based superalloy as well. So in the today's presentation, we will be focusing mostly on the mechanical and functional behavior of nickel titanium-based shape memory alloy, particularly in the submicron scale. Okay, so with this basic overview of my group activities, let's move on to the material. Now, this is a very fascinating material, and let me just start the presentation with this note that this is the first day of this FDP program, and you are visiting from different places or attending this program from different places. You are going to listen to many of the talks, which would be, I'm sure, will be very, very informative and will be used in your area of research or academic activities, certainly. So you are going to remember the major takeaway from this program, right? And today I'm going to start this session, the first day, with a material that can remember its shape. So like you guys who are able to remember many of the things which are important, this material also is a very fascinating one. And even if we do whatever change to its shape, it is still able to figure out what its original shape was and can go back to that shape. So it was first discovered by Olander long back, almost a century back, in 1932, and later on, so these are all Au cadmium based alloys, and first time when I say shape memory alloy, it is very commonly also known as Nitinol. Many of you might have heard this term either NITI or Nitinol. So Nitinol comes from the name as nickel titanium, which is found at Naval Ordnance Laboratory at USA by Bueller, and that's how the name Nitinol has been publicized in 1963. And by 70s 80s nitinol has been used as biomedical implants, and by 90s it is being used in not only in medicine but also in other applications, particularly as sensors and various others, aerospace, robotics, various kind of niche application areas. Okay, so shape memory alloy is one such material which is used in different kinds of application, very niche application, starting from human body right to the space. So let me just show you some glimpses of where this alloys are being used. So these are some of the applications in the field of biomedical engineering. So this is used as the plates or the hip replacement. Very popularly used as cardiovascular stent. You see, this is a picture of a stent made of nickel titanium, and it can do, it is having much better performance than the commonly used steel, which is used as a stent material. Also, it is recently been finding application as orthodontic arch wires. So you see, this kind of arch wires are used to shape up the teeth properly, particularly seen in young kids and teenage boys and girls. And it has been found that nickel titanium is perfect in shaping up the teeth, maintaining the oral shape of individual person, and can change it accordingly. So it is considered as a much effective and beneficial material in comparison to what that is typically been used, like stainless steel. Okay, these are the some examples of the replacements as well as the robotic arms where nickel titanium is finding application. Okay, so this is just a small video of how it works as the cardiovascular stent. Let me just play this. You can see that this is an artery which is clogged by cholesterol or some other thing, and then we can insert a stent which, due to application of temperature as well as stress, it can expand, remove the clot to some extent, and the blood flow can be regained. Okay, so this is how nickel titanium is used as a stent and finding popularity. But not only restricted to this, it is also used in the field of aerospace and robotics a lot. So this is an example of the GE engine where shape memory alloys are used here as in the form of beams. These are some of the examples where it is used in the robotics. Shape memory alloy also used as sensors, where it can automatically cut off as the temperature is reached or a certain stress level is reached, etc. Now this one I found very interesting, especially since this faculty development program aims on the aerospace engineering. So this is a smart structure built by NASA and is still under research thing. But you can see that how it imitates by using the shape memory alloy in an aerospace structure. It can imitate how the bird used to fly, and a same kind of maneuver and control can be obtained if we are able to use shape memory alloy in the wings of an aircraft. Okay, please let me know, is there any sound coming with the video? Is the audio working?
No, ma'am.
No, ma'am.
Okay, then Professor Tamilvendan, you have to help me how to include the audio.
To include the audio, actually, we have to play through Google Slides.
No, I am sure it can be done from here itself. Actually, these days for the class and everything, we use Microsoft Teams. So I'm very well aware of that, but somehow the Google Meet thing, I am not able, but I remember doing it somewhere from the settings, which...
1 minute, ma'am, let me see.
Yeah.
Ma'am, can you just play the video?
I guess the audio is still not coming. I can do one thing. I can unshare and then share one more time. If is that okay?
No, it's not audible, ma'am.
Yeah, it's not audible. So let me just unshare this and try to figure out if I can share the sound as well.
I think instead of sharing a particular tab or window, if you share the entire screen, you can able to play the audio.
Okay, is my screen visible?
Yes, ma'am.
Okay, but I still could not find a way to cast the sound, and that means many other videos won't be able to be
Excuse
heard.
me, ma'am. Your voice is echoing.
Okay. Yeah, is it okay now? My voice?
It's still echoing, ma'am. Actually, in case if you are playing it from two systems, you can mute.
I am not playing anything. Like everything is off.
One minute, ma'am. It's fine, ma'am. Now you can go ahead.
Okay, fine. Since you cannot, so there is not much in this video to here. So this just, okay. This just shows that how with the application of nickel titanium, the wings are able to change its shape, and this will help for a better maneuver. And you can see this is a mesh made of shape memory alloy, and with temperature, this undergoes different kind of shape changes, and that leads to such kind of behavior that it can change its the shape of the wings. Okay, now this one here on the right side is another very interesting application of nickel titanium. Now this is used in lunar rover. So the rover, the vehicles that is used in the moon. So you know, moon has a very rough terrain, and for that, again, NASA has made a wheel made of the mesh of nickel titanium. And you can see that how it can overcome any hurdles that come on its way, and still there is no damage on the wing, on the wheel frame. So you can see that it can easily pass through different kind of terrains, and made of nickel titanium alloy, which can undergo a huge amount of deformation and yet can come back to its original shape just when it is being removed from that rough terrain. So this is also known as super elastic. So earlier it used an aluminium wheel, and there was a significant damage that has been noted in the wheels. So it was made in 1960s, and that could not hold much of a weight. So there was further development, and then it was made used in the Curiosity Mars rover. But then significant damage has been incurred on those wheels. You can see the wheel structure there, completely different from the present one. So now this one is the latest design of the lunar rover wheel that has the ability to move smoothly on any kind of terrain with whatever rough it is. So this will be used 2 years from now in the Mars mission. Okay, so various ambitious activities are going on. So this you have seen the extreme usage of nickel titanium for very niche and high-end applications. And now let's see where else this can be used. So nickel titanium is also, or shape memory alloy, not only nickel titanium, shape memory alloy polymers are also very much used in the field of textiles. Now this is used in not only in armor jackets, but several other kinds of cloth materials. And you can see this as an example. This is a cloth made of a shape memory alloy fabric, and this can automatically squeeze or expand depending on the temperature. Okay, they can automatically roll up if the temperature is changed. So this is very fascinating and can be used in different kind of applications. It looks like a magic one. Okay, so just by spraying the warm air, it is possible to squeeze the cloth. Okay, so then the obvious question that comes to anybody's mind is why, how, right? So how can this material remember its shape? And to answer this question, I should also emphasize on something called phase transformation, which once again many of you will be aware of. But for those who are not very familiar with phase transformation, this means that how the crystal lattice is being changed. Okay, so initially this material is made of a structure which has some kind of lattice arrangement like this. Okay, in case of nickel titanium, this austenite structure, this phase is called, the starting phase is called austenite, and this, in case of nickel titanium, this austenite phase has a structure, as a cubic structure. You can see one of the atom, let's say the nickel atom is sitting at the body center, and the titanium atoms are fitting at the corners of the cube, and so on. If we are applying now temperature, or if we are reducing the temperature or applying stress, or both, then this crystal structure can change to a completely different one. Now this one is having a monoclinic structure. Same nickel titanium atoms, nickel atoms and titanium atoms, the red and the blue ones, are rearranged in a different kind of lattice, and this leads to all those magics that are coming into the place. Okay, so the cubic structure, the dashed one or the solid one, is a cubic structure which can change to a monoclinic one, and that leads to all the differences in the properties that can come into the picture. So this one video once again shows that how the activities of nickel titanium are working, and or the shape memory alloy in general, and how shape memory alloy structure can be formed. But unfortunately, if the sound is not audible, I will try to explain this as much as I can. Okay, this is not audible, right? So let me mute it. So this is warm water, and whenever a shape is, a wire is placed in that warm water, it gains its particular shape that has already been set to it. So you see, these are the different phases. This one is ice, and this is water, and then the boiling one, you know about the vapor. So these are the three different phases of water. So similarly, for nickel titanium also, as I have shown, that there are two different phases, austenite and martensite. And all this is by the placement of the atoms into certain crystal structure. So in case of ice, there is a hexagonal one at very low temperature. So in case of shape memory alloy, this low temperature phase is martensite, and at high temperature, it automatically changes to this cubic structure. And how to set the memory shape? So you can see that how the wire is being plugged into the screws. So particular shape is being given, and then we need to heat it to certain temperature, at which it is fully austenite. Okay, so at high temperature, this structure is having an austenite shape, and it is able to remember that shape. And when we are cooling it or quenching it in water, it changes to martensite phase. Okay, now when it is at the room temperature, at low temperature, if we are changing the shape, it is in the martensite, and whatever is happening to its lattice, it will come back to the austenite once it gains the temperature back. So as soon as we are giving it to the high temperature, you see the martensite structure has changed to austenite, and it has regained its shape back. So different kind of predetermined shape can be obtained if we are just changing the temperature and giving it to a different shape. So this is called the shape memory effect, and now we are talking about the super elastic effect. As the name suggests, it's like elastic, so more than elastic. Unlike the regular one, it has even higher elasticity or recoverability, but that is not by elastic deformation, but due to the phase transformation. So at higher force, and we are changing it to martensite, and when we are removing the load, it is coming back to austenite. So this is for an eyeglass application, the frames of the spectacles, which we can bend and twist in whatever way, and it is not going to have a permanent deformation or break for that matter. Okay, so this is how we would like to look into the more details of any kind of deformation or any changes that are happening. We would like to look into the atomic changes that are responsible for such kind of differences in the properties. Okay, now shape memory alloy is not only showing such changes in the shape, as you have seen that we are putting it in warm water and we are getting a particularly pre-designed shape. It is not only restricted to that. Rather, we can have a two-way shape memory effect, and what it means is that we can have two different shapes set in this one. In the austenite phase, when we are setting a particular shape, and then in the martensite phase we are again setting another shape, and then just by changing the temperature or by applying the stress, we can it can come back to and fro to two different shapes. So obviously this is used for several applications where we can make use of two of the different shapes of this. So you can see that this one is the cold one, this one is the hot one, and the spring has a particular length in the cold and the hot one, and it automatically goes to that kind of configuration whenever we are changing just the temperature. Okay, so one might be set in the low temperature, one might be set in the martensite phase, and the high temperature one is set in the austenite phase, and it can go. So this one is also very interesting to watch. We simply can change the temperature at the tip of the spring, and you can see it is coiling or uncoiling on its own. See, it is doing this on its own. On the water, it is attaining some shape or some length, and then as soon as it is being taken up from the water, it is regaining its previous shape. So this kind of things are used in the sensors, in the thermostat and all, where there is an automatic cutoff, they can be used. Okay, so now there are different kinds of shape memory alloys. Okay, there are particularly metallic shape memory alloys. If we are talking about, there are iron based, copper based, and nickel based, nickel titanium based shape memory alloys, which are very commonly found. And here I'm just showing you a comparative study of the different kind of shape memory alloys. This one is the nickel titanium, these two are the copper based, and the last one is the iron based. And if you look into all the properties, we can understand that nickel titanium based shape memory alloy give a optimum combination of properties. First of all, when we are talking about shape memory alloy and any material that can recover its shape, we are mostly interested on this term here, the recovery strain. right? You can see that the recovery strain is quite high for the case of nickel titanium in comparison to that for the copper or iron based alloys. And if you might wonder that what is the recovery strain for any regular metallic system, it is actually less than 1%. Okay, much less than 1%, sometimes as low as 0.1% or 0.3%, something like that. But instead, in case of nickel titanium, it gives to such a high value of around 8 to 10%. That means that if the material undergoes deformation by 10%, it can come back to its original shape and regain its 10% deformation back due to its pseudoelastic properties. Apart from that, it also has the elastic modulus, which is quite in the range of around 70 to 100. So that is what we can see for mostly all of the material. Most interestingly, what we can see here is that the martensite phase is having the elastic modulus, which is quite similar to that of human bone. And all the applications of nickel titanium as biomedical applications, you can see that one of the reasons that nickel titanium is very much popular is because of its low elastic modulus in the martensite phase, whereas the other alloys, you can see that these are having quite higher modulus of elasticity even in the martensite condition. Okay, I think the microphone is not muted for one of the participants. Kindly mute yourself. Okay. Fine. So apart from that, strength and elongation are also quite high for the case of nickel titanium, and quite optimum values that we can obtain, and that is one of the reasons that nickel titanium has gained the popularity over all different kinds of shape memory alloys. And not only that, if we are talking about the temperature range over which it can be used, you can see that nickel titanium is typically used for very low temperature up to around minus 50 degree to plus 100 degrees centigrade, but quite a good span of temperature which is used for regular usage. If we want to use it at a higher temperature range, we can make a ternary nickel titanium alloy with the addition of hafnium or zirconium or platinum, and we can achieve a temperature as high as 300. So overall, we can achieve quite a range of temperature starting from minus 50 to plus 350 or 300. That is quite some high range of temperature that can be obtained. On the other hand, copper-based alloys are mostly high temperature, and we cannot use it for low temperature or room temperature application. So all this have made nickel titanium very much important. You can see that this the importance of this temperature. So this material at high temperature behaves like a regular material, like any other metallic system, and like an elastic plastic one. Whereas at intermediate temperature, it has a pseudoelastic effect, and at low temperature, it shows the shape memory effect. Okay, and all these are occurring because of the phase transformation that this material undergoes as the temperature is being changed. So even if we are not applying any stress or anything, just by changing the temperature, the phases change, and that leads to all different kinds of properties and different kind of characteristics for this alloy. Okay, at high temperature, we can see the pseudoelastic effect, whereas at low temperature, comparatively low temperature, we can see the shape memory effect to be active. So these are the principal advantages of choosing nickel titanium over other kind of shape memory alloys, is that it has a temperature of applicability around minus 50 to 110 degrees centigrade. Quite good number of strength, and elastic modulus is also high in the austenite phase, but in the martensite phase it matches to the human bone. Along with that, this material is biocompatible and have good corrosion resistance. Okay, so that makes this alloy very much suitable for biomedical application, whereas it has a very high damping capacity because of this recoverability, and as a result, in the earthquake prone structures, also in bridges or flyovers, so there also where damping is one of the main factor, nickel titanium is being used. Okay, so this once again is the properties of nickel titanium, overall properties of nickel titanium. So I'm not going through the details of this, already talked about this. But before we go into the nitty-gritties of nickel titanium and the explanations, I would like to give a hint of what are the different terminologies that are used in the shape memory alloy business. Now, you must have heard about these terms some way or the other, like shape memory alloy, obviously, and often known as SMAs. And not only that, this material is known as memory metal because it can remember its shape, or smart metal. And Nitinol, as I said, is a very common name for nickel titanium. Now there are shape memory effect, as you have seen in the video, and this effect, the shape memory effect, is related to the temperature change as well as the stress change, both the change in the temperature and stress. But there could be just one-way shape memory effect or even two-way shape memory effect, where it can able to remember two different shapes. On the other hand, it also has pseudo-elastic effect, also known as super elastic effect. As I said, that it can recover its strain up to as high as 8 to 10%. Okay, now all these kind of effects, shape memory effects or pseudo-elastic effects, are related to the phase transformation, and in any kind of phase transformation, there is a parent phase, which is nothing but the austenite, and a product phase or daughter phase, which is martensite, or R phase is also another intermediate phase. And then there is tween, detween, or reorientation. This kind of things also happen, particularly in the martensite structures. And the phase transformation from this austenite to martensite, or parent to product, occurs along certain pairs, certain variances. Okay, so these are called correspondent variant pairs and habit plane. So I will just explain this in a bit. And all this kind of phase transformation is not arbitrarily happening. So there is a theory behind it. There is a stress-induced martensitic transformation that is happening, and there is a phenomenological theory of this kind of transformation. So these are the words, the jargons that are very much used in the shape memory alloy business. And I thought would share this with you. Okay, now coming to the real picture, how this is happening. Okay, we have seen this earlier also. So there is an austenite structure, there is a martensite structure which converts from austenite to martensite. So far is so good. But how this conversion is happening? You see that when a cubic structure, the dashed one here is a cubic structure, okay, and the orange one is the martensite structure. So when this parent phase, the cubic phase, converts to martensite, it can happen along different variances. And there are actually, in case of nickel titanium, there are 24 different correspondent variant pairs. So this transformation can happen through any of one correspondent variant pair. Okay, just one out of 24 will be selected, and this selection is done based on the energy criteria. Okay, if we have different grains, like in a polycrystalline materials, this transformation can happen through different CVPs for different grains. That is also possible. But whatever it is, one set of transformation from one austenite single crystal to another martensite single crystal can happen along one out of 24 different CVPs. And in whichever way it is happening, there is a habit plane, which is a common plane between the austenite and the martensite. Just checkered plane here is the habit plane. Okay, so then once this conversion from austenite to martensite is done, then if we are applying the stress, there is a detwinning that happening. So initially martensites are formed as twins, and if we are applying the stress, it is kind of getting stretched up like this. I have shown with the Venetian, the cartons, that you can understand that if we are applying it, if we try to stretch it, it gets stretched. Similarly for the martensite twins also, if we are applying stress, it detwins, or this is also known as reorientation. Okay, now what happens when we are simply applying stress is that initially there is an austenite structure. Okay, so this structure here is a cubic one austenite structure, and when we are applying stress, this is a typical stress strain curve that you're familiar with. When we are applying stress at a particular amount of stress known as the Martensite start stress, this austenite structure starts converting to martensite. Okay, and by the end of this level, this can be either flat or with a very little slope. This martensite conversion is complete, and there is a detwinning also has happened. You can see that initially this is twin structure and later on it is getting stretched. Okay, now the beauty is that up to this level, if we have applied the stress and it has attained certain amount of strain, and now if we are simply unloading it, it comes back to the initial starting phase, that is the austenite phase, and this entire amount of strain gets recovered. Okay, so that makes it an interesting system. So this is how the stress strain curve looks like. You can see the elastic part like any other material, and then the pseudoelastic part and detwinning, etc. If we are unloading it from here, it will come back to the austenite phase, but if we are keep on adding stress, it will behave like a regular material. So this is like the typical elastic plastic deformation, and it will fracture at certain point. Whereas if we are unloading it within this plateau region, this is known as pseudoelastic plateau, it can regain its shape completely. So this is the experimental results that we have seen in our group. Okay, now this everything has been done without the application of temperature, or with keeping the temperature constant, isothermal condition. Now there can be another situation when we are not making any change to the stress level, but the temperature is being changed. So initially the alloy at higher temperature is austenite, and then when we are cooling this, there is a phase transformation happening. Starts at the martensite start temperature, finish temperature, etc. And this is the differential scanning calorimetry curve, again the experimental curve, and you can see that as we are heating the specimen back, at certain point the martensite is being converted to austenite once again. So there is a start and finish temperature, and once it reaches the higher temperature, it is back to the austenite phase once again. Okay, now pseudoelasticity is our main topic of concern for today's presentation. We'll be talking about how this material behaves and what are the differences in the pseudoelasticity if we are playing around with the material composition or the making of the material, processing conditions, etc. So this is how the pseudoelastic thing looks like. We have an initial structure, as you have seen, made of austenite, and then if we are applying stress, it extends or attains a different kind of shape, and then when we are releasing the stress, it comes back to the original austenite form once again, as seen from the bottom image here. Okay, same thing is being explained here with the atomic changes. Now, let's come to some of the experimental results. So what we have seen in this study is very interesting. So we have a nickel titanium rod, something like this, of around 10 millimeter diameter, okay? And it shows very good elasticity in tensile sample as per the standard. And then when we have tested this tensile testing, you can see that this one is the compressive stress strain diagram, but you can see that it can undergo the phase transformation, and the load, once it is being removed, whatever strain that has been generated, that is completely recovered. Okay, now we understand that, okay, this is the bulk properties of the material, but what happens internally is even more interesting. So what we did is, we did a detailed microstructure study at the first hand. So you can see here, this colorful image is nothing but a electron backscatter diffraction image. Okay, it's called IPF map, inverse pole figure map. Okay, you can see the grains of different orientations very clearly, and all these are nothing but the austenite grain structure. Okay, this is the crystal structure of austenite. Based on this, the different orientations, the different grains are being colored. Okay, this is the TEM image, and you can see that this is very nice, the grain boundary and the triple points here, and this is also confirmed. The crystal structure of the austenite phase is confirmed through TEM. And okay, we are all satisfied that this is a single phase material. This is also confirmed by the XRD, X-ray diffraction, and which shows a single phase material with the austenite structure having B2 phase. Okay, this B2 is just the cubic phase, ordered cubic structure. Now, when we did the DSC, differential scanning calorimetry, we could figure out that what are the martensite start and finish temperature and what are the austenite start and finish temperature. Now, you can see that the martensite start temperature is minus 23 degrees centigrade. So that means that if we keep on cooling the alloy from room temperature or 150 degrees centigrade here at minus 23 degrees centigrade, it starts converting to martensite. And when we cool it till minus 150, it is fully martensite. And again, when we are heating it, it starts converting to austenite at around minus 12 and finishes at around 3 degrees centigrade. So that means that at room temperature, this material is fully austenite. Okay, room temperature means 30 degrees centigrade temperature. It is fully austenite somewhere here. Okay, fine. Now, what we try to do is we try to find out the pseudo-elasticity of each of these grains. And how we do that, since the grains are very small, size of around 30-40 micrometer, we did indentation. Indentation, as you can see in this small video here, so what it does is, it has a specimen surface and then it indents on it, it presses, and once it comes back, we get an impression of this indenter. Some part will be recovered and some part there will be a permanent deformation. So this is the force versus displacement or depth of penetration diagram curve, where you can see that we force the indenter up to certain level, and then when we are unloading, it is not coming back to the initial position, but there is some kind of elastic recovery and the rest is plastic. Okay, so from this kind of pH curve, indentation load versus indentation depth curve, actually we can do a lot of studies. We can find out the elastic modulus of the sample. We can find out the hardness of the sample, of the material. Okay, so we have done all these things. Now, in case of shape memory alloy, very interestingly, it will show a pH curve something like this. Okay, so you can see the red one, which is fully plastic. Okay, so this one here, A prime, B prime. So this is fully plastic. And this one here, so the entire thing, the green and the yellow part, entire part has been recovered. So this is what is the recovery displacement or depth of penetration for the case of nano indentation of nickel titanium. Now, out of that, the yellow part is the elastic one because it follows the elastic modulus, and the green one is the pseudo-elastic one. Okay, so based on this understanding, we did indentation on different grains having different orientation. So these are some of the examples shown schematically. Actually, the indents are very small and cannot be seen with in any microstructure or microscopy very easily. So again, what we are going to get from here is something like this, the elastic and the pseudoelastic zone for the case of nickel titanium. Now, for comparison purpose and for you to appreciate that how the deformation is supposed to be in case of any other material, this is one for the case of steel and using a different kind of indenter. And you can see here the recovery strain is only this one, okay, compared to the entire gray plus orange part. We have just this part as the total recovery. Okay, so this is the beauty of nickel titanium alloy, and to our surprise, what we found is that when we did this for all the different grains, you can see this is a stereographic triangle, and the colors here signifies the color of the grain that we have seen in the EBSD map based on this orientation. So we have indented on several orientations, okay, and we have found that the recoverability of these grains are different. These orientations are different. Okay. So you can see the pH curve for three of the representative orientations that I'm showing you today. So these are the HKL values, different grain orientation. You can see that there are for three different cases, and we see a complete difference in their pH curve, the load versus depth curve. You can see the blue one is almost, it's coming back to its initial phase and there is not much change. Whereas we can see a significant change in the shape of the blue curve. The red one here is how it is supposed to be when it is completely elastic one. And there is a huge amount of deviation when we are talking about this orientation, which deviates completely, and there is a significant amount of plastic deformation here, permanent deformation. This becomes more apparent if we are able to find out the stress versus strain curve. You can see that it shows some kind of features similar to the pseudoelastic behavior. There is a plateau strain and there is some further deformation as well. But here there is a huge amount of strain that is not being recovered at all. So that means that the different orientations will behave differently. Okay, as I said, that different orientations may also undergo the transformation based on different CVPs. So this is very important if you are talking about fabricating a single crystal, let's say sensors. Okay, we would like it to have the best pseudoelasticity, and we cannot cannot ensure that unless we know that how which one is actually supposed to give us the best pseudoelasticity and which orientation is not suitable for pseudoelastic recovery. So based on this kind of detailed study, we have done this on hundreds of grain orientation to figure out which one is the easy orientation, that means which shows the best pseudoelasticity, and which one is the hard one. So the take-home message from here is that grain orientations do influence the phase transformation characteristics and the pseudoelastic recovery. And if we are thinking of using it for a single crystal application, we should be careful about that. Okay, someone made a question which I hope I can answer after the seminar. Okay, so let's now move into another important aspect, which is the effect of processing conditions. So in this case, we are just simply aging the alloy. Same starting rod that I have shown earlier. Okay, now what we are doing is we are performing some kind of aging to this alloy. And let's see what it does to its pseudoelastic characteristics. So once again, this is the stress strain curve that it is supposed to show with a complete recoverability for a bulk specimen, right? Now, this material, when we are trying to age, we have something in mind. We understood that if we are aging it at a temperature higher than 300 degrees centigrade, it is supposed to form some precipitates. Okay, some nickel-rich precipitates like Ni4Ti3, something like that is supposed to form. So obviously, microstructure is changing, phase is changing. Now, let's see what happens to the pseudoelastic characteristics. Before that, we are coming back to the initial microstructural study. As I said, all the properties are finally related to their microstructure. So we always start from the microstructure itself. Now, in one case, we have a homogenized alloy, which shows the same picture that I have shown you earlier. So this shows a perfect austenite structure. And in other case, where we have aged it, excuse me, at 550 degrees centigrade for 2 hours, we can see that there are the presence of precipitates. We can also see some presence of martensites in the structure. It is lath kind of structures. This could be martensites. Okay, now these precipitates are very small, around 6-7 micrometer, and lenticular, acicular kind of structure. Okay, when we did the XRD, unlike the homogenized one, which is made of fully austenite structure, in this case, we find the existence of not only martensite but also precipitate in the XRD itself. So even if we are not visualizing it, we are able to find out the martensite and the Ni4Ti3 precipitates right from the XRD itself. Okay, fine. So now the structure has been changed. So let's see what it does to the thermal treatment behavior. So, you know, because of the presence of this precipitates, the phase transformation from B2 to B19 can happen. So this is what we have seen. For the case of homogenized one, we see a typical austenite and the martensite structure conversion, as we have seen that the austenite finish temperature is only 3 degrees centigrade, so much below the room temperature. In this case, on the other hand, we can see that the temperatures has been changed and there are double peaks in case of the cooling cycle. So there is the R phase conversion first, which then converts to martensite. And finally, this R phase conversion starts at 0 degree, and the austenite finish temperature is something like 30 degrees. So it's very close to the room temperature, or if we are considering room temperature as 300 K, actually it is exceeding the room temperature to a certain extent. So that also indicates the possibilities of presence of a little bit of martensite at room temperature. Okay, also these double peaks do signify that there are precipitates present in the structure. Okay, now to figure out the pseudoelasticity, we used a smart way in which we, of course, did indentation, nano indentation, but we used two different kind of indenter tip. In one case, this is the Barkovich indenter tip, popularly known as Barkovich, very commonly used for nano indentation. If you want to use nano indentation, this is the most preferable indenter tip geometry. Okay, it gives a triangular shaped impression once we indent it on a material. Along with that, we have also taken a spherical indenter tip, which, as you can see, the tip is quite blunt. Why we did this, why we use two different kind of indenter tip, is to make sure that there is not significant amount of plastic deformation. We can still impose very low amount of plastic deformation to figure out any differences in the pseudoelastic recoverability, if there is, amongst the homogenized condition as well as the precipitated condition. Okay, so to see that, you can see now this is the spherical indenter one only, and you can see that there is a significant difference in the indentation load versus indentation depth curve, isn't it? The blue one is for the precipitated one, as well as the green one is the homogenized one. And you can see it clearly that the green one and the blue one has a completely different picture. Now this becomes more apparent if we are doing the stress strain curve, and here actually the image indexing is a little bit different, which shows that the blue one now is the homogenized one and the green one is the precipitated one. Okay, but you can understand it very well. The swollen one here is nothing but this one there, but there is a complete differences in the stress strain behavior of this. In fact, the green one, the one with the precipitate, has required much lesser stress for the transformation. From austenite to martensite, and it can show a plateau region also very distinctly. So this once again has shown that presence of precipitates. So same alloy content and everything, and also we are not here talking about the orientation or anything, even if on the same orientation, just if we are having the alloy aged. So if there are precipitates forming on the structure, that can also influence the phase transformation behavior and the pseudoelastic recoverability. Okay, so the point is that if we want to achieve the best combination of properties, and best combination means the optimized condition. Sometimes we have to rely more on the strength, sometimes more on the recoverability based on the application. We can play around with the microstructure, we can do some changes in the processing conditions, and we can achieve completely different kind of properties that should meet our requirement. Okay, so am I going too fast, or is it okay so far?
It's okay, ma'am.
Okay, fine. So let's move on to the last but not the least topic that I'm going to cover in this seminar. So that is the, again, since I have talked so much about processing condition, like if you're aging it, something else is happening. So let's see if we are doing additive manufacturing, what else is happening to this alloy. And So before going to the details of this this part of the talk, let me make things a little bit clear about the manufacturing process itself. So what we do in a regular material when we want to make a component of certain shape, dimension, etc., we use a conventional procedures of casting and different kind of machining operations. Okay, so we use drilling, grinding, etc., different kind of machining operations, as you can see here. So here is a video which shows the different kind of operations that are being done. So we use a cast shape, a billet or something, and then depending on whatever is the final structure, we try to machine that out. Okay, since the audio is not visible, okay, you can see that this is the tool and this is the, okay, and there is a chamfering that's happening. So it's a turning that is happening, and you can see that the material itself is turning and it's giving a shape. So this is a taper turning that is happening, and it gives a taper here, like this, a taper. Okay, now this is a contour, and you can see that depending on the design, the kind of contour that we need, this looks like a doorknob, and you can see how smoothly it is being machined. Okay, but also at the same time, you should pay attention the amount of chips that is being generated on each time it is turning it. Okay, so this is going as scrap, going as a wastage in most of the cases. So this is forming. So when we give a particular shape directly, so the corner here will be chamfered. Okay, so these are the chips that are coming out, and now you see there is a 45-degree angle that has been formed. This is grooving, where the groovings are being made, threading, etc. All different kind of shapes that we need to provide. We use such kind of subtractive. This is known as subtractive technique or conventional technique to make that. Okay, so in short, this is how it is formed. We have a big block, and then we use the subtractive manufacturing. Subtractive because this is continuously being removed. Okay, and finally, whatever structure we require, this is the shape which is given, and there is a huge amount of waste, almost similar amount, sometimes even more than the actual object. Okay, in contrast, when we are talking about additive manufacturing, this is a layer by layer addition which gives to the final 3D shape. So we use whatever material is required, only that much amount, and then it is formed from the in the bottom up approach. That's why it is called additive, because each of the layer is being added up one upon another, and we finally get the same shape as this one. But in this case, you can see that there is a very little wastage. So obviously, additive manufacturing saves not only the material but also the cost. It is a green technology, good for the environment, and so on. And also, it is giving a complicated shape, that too in. Okay, getting distracted by some questions. Fine. So these are the typical differences between additive and the subtractive manufacturing. So in this case, the additive manufacturing, material is added layer by layer to form a complex shape just in one step, and there is a possibility that some porosities may generate. Okay, but whatever it is, that can be controlled and monitored. So there is a significantly reduced material wastage, as we have seen. However, the only drawback that we can think about of additive manufacturing is that it is still now applied for a very limited number of materials, whereas subtractive manufacturing is used for a widely different kind of materials for ages, and in this case the material is removed from the solid block to give a complicated shape, and as a result it leads to a significant amount of material wastage, but it also generates differences in the density or porosity, and it is a little bit difficult to control the porosity generation, right? So this you can take as the advantage of additive manufacturing and the disadvantage of subtractive manufacturing and conventional manufacturing, whereas the advantage of conventional manufacturing is that it is tested and trusted for many of the materials for decades, for ages, for centuries. And in this case, the additive manufacturing is a growing technology, and a lot more needs to be known for applying this on a bigger scale. So these are some examples of additive manufacturing processes that are used for different metals. Different materials. For metals particularly, we use either of these techniques, powder bed fusion or powder feed and technique. Okay, and there are again different categories of powder bed fusion, where the powders are okay, thank you. So in case of powder bed fusion, the powder is spread in a bed, and then the particular shape, based on the particular shape and dimension, laser is acted upon that to give it a typical complex shape that we require. And in powder feed, there's the powder and the laser source are being acted simultaneously to give the particular shape as per the CAD, computer aided design policy. Okay, so there are different kind of technique like EBM, DMLS, okay, SLM, which are very famous for powder bed. And in case of powder feed, there are this laser engineered net shaping known as lens, direct metal deposition, laser metal deposition. These are some of the very popular techniques. And today's presentation, we are going to talk about the lens, laser engineered net shaping process. Okay, so let's see how this kind of process works. So what happens here is that powder is inserted through one of this nozzle. Sometimes there are two powder feeders also, and in this case there are two powder feeders, this green one, and then there is a laser beam which are acting simultaneously, both the powders and the laser, and this can move based on the CAD design, and that can lead to a final shape. So you see that here it's a video which shows how this works. So you can see that there are these dual powder feeders. Here is the laser tip. Okay, so you can see now how these are the parameters set on the machine. Laser is being on. And this is how it is being formed. You can see the powder feeders and then the laser, and this is moving, scanning kind of as per the design. Okay, so it's moving in this direction, and in the next layer you will see that it is actually moving in a perpendicular direction. Okay, so now you see it has changed its direction of moving in a perpendicular one. Okay, so every layer it can alternate its direction of motion, and this can be set if it is 90 degree or 45 degree, 60 degree based on the requirement. That is to maintain some uniformity in the structure so that it is not getting textured. And once formed, it is removed, and then the substrate has to be removed. Okay, so this is a machine placed in the Central Glass and Ceramic Research Institute, which has been used here. So all the operations are done inside the glove box. Okay, now when we made 3 coupons of nickel titanium, what we did is we varied the parameters of the additive manufacturing here. So we played around with the power and the scanning speed, and we end up having 3 different laser energy densities. Okay, one having the lowest laser energy density is 27 joule per millimeter square, as well as the highest one is more than 3 times of this, which is 70 joule per millimeter square. So this is a starting powder is same, but we just use 3 different energy parameters, and as a result we end up getting 3 coupons which looks alike. We all know that it started with the same material, so it's supposed to behave the same also. But what we have seen is interesting. So this is the coupon that we have formed. This is a schematic of that, and you can see that this is a schematic of the layer by layer structures formed. And since this and the subsequent layers are in the alternate direction, so you actually cannot, so this looks blank, but if you go in the perpendicular to that, you can see the opposite patterns here. Okay, now it's a complicated microstructure that it is supposed to form because of this layer by layer addition. And to figure that out, we actually have done the microstructural analysis at the top, middle, bottom, front, back, at the cross section, everywhere. Okay, and what we can see is this is just the optical micrographs, but the tint edge that gives the different colors, which makes the different layers very clear. Okay, not much difference could be found here, but this layered structure, this is the EBSD one. This shows that this is a layered layer by layer formation process that has been used. Okay, so still no clue about the differences in the microstructure. Okay, someone has muted me. I realized Kirtivasan R has muted me. I hope I'm now got back by voice. I am not sure when he or she has done that, but please refrain yourself from manipulating my screen. Okay, I hope I'm audible now.
Yes, ma'am, you're audible.
Okay. Okay, so this is the optical microstructure, and you can see that within this layer, so these are the layers, okay, you can see the layers very clearly, and within these layers also we have structures which looks like a loop, and this is nothing but the way the laser has been tipped around. So this signifies the tip of the laser. Okay, the difference between these two tips are known as the hatch spacing, and we can also figure out the layer thickness from this. So that is what we have done in details. We have taken a montage of several images to figure out what is the layer thickness and what is the hatch spacing of the structure. Okay, now if we look into this more carefully, we'll see that there are different kind of grain structures that are forming inside this optical micrograph. You can see that there are these columnar grains, you can see that there are some kind of equivox grains, and then there are fine equivox grains, and so on. So we have estimated the size for each of this, and you can see that there is a, while the columnar and the equivox grains are as big as 25 to 30 micron, the fine equivox are only 4 micron. So there is a huge non-uniformity in the structure. And interestingly, this non-uniformity is also getting reduced as we are changing the laser energy density. Okay, so not only that, there are some phases which are extra, like the precipitated phases, which are forming when we are applying the highest laser energy density. Okay, this is shown in the TEM studies. What we did next is, for these coupons, we have done the micro computational tomography. So it shows the porosity, presence of porosity in a 3-dimensional way. Okay, so you can see how the porosities are distributed throughout the structure, throughout the coupon, and you can see that they are mostly internal pores, and it is important to know the presence of the spores and how these are being changed if we are changing the laser energy densities. Okay, so this one is prepared with the lowest laser energy density of 27 joule per millimeter square, and this one is prepared with the highest laser energy density. So this is very much obvious that the one prepared with the highest energy densities got enough time to melt and fill up those voids and all, and it leads to significant reduction in the porous structure. Okay, in the XRD, we have seen, so we have done the XRD for the starting powder as well as all these three lens manufactured alloys, and we can see that the one manufactured with the highest energy, as you have seen from the TM, this also shows presence of precipitates and martensite phase, and this is reflected in their DSC pattern, their phase transformation temperatures as well. So the one prepared with the highest energy density shows very high austenite finish temperature, which indicates that the room temperature is having martensite phase. Okay, now this is supposed to play around with its mechanical properties as well, and we started with indentations at the first, and we did indentations at all different levels. At macro indentation, when we use quite higher load of 500 Newton, you can see that it has almost similar values of hardness for all the three conditions. Okay, when we did micro indentation also, we have seen more or less, not exactly the same, but within the scattered level for the three conditions. Okay, E1, E2, E3, almost similar values are obtained, even if we are varying the load levels. But when we are doing the nano indentations, we can see that there are differences in the values of hardness and elastic modulus that we are generating for the one prepared with the lowest energy density and the one prepared with the highest energy density. Certainly, the microscopic level of the different phases that are forming lead to such changes, which can be assessed like nano indentation. Okay. So again, we did spherical nano indentation to figure out the depth recoverability, and we found that the one prepared with the highest energy density actually shows the least recoverability. Okay, this value, this signifies the permanent deformation, the extent of permanent deformation. A remnant means something that is permanent, that is not going up even if we are unloading. So that remnant depth ratio is highest for this E3. But interestingly, what we found is that this E2 alloy, so prepared with an optimized value of laser energy density, this one shows a very good value of recoverability. So this one shows around 90% recoverability. You can see here with the green colored curve. This shows a very good amount of recoverability. And to check that, we have plotted the stress strain curve for these three alloy. Once again, the one E3 prepared with the highest energy density, because of the presence of martensite and precipitates, that restricts the recoverability, and there is a huge amount of plastic deformation. And to our savior comes this alloy prepared with optimum laser energy density in the middle, which shows a perfect pseudoelastic plateau and so on. Okay, now to find this out completely, we did the macroscopic tensile test, like the regular conventional standard tensile test, and you can see that for the one with optimized laser energy density actually gives the highest deformation, and we can figure out the pseudoelastic plateau also very clearly from this structure. To check for the recoverability, we did the cyclic tensile test also. This blue one here shows significant amount of recoverability. To check that further, to confirm that further, we have done the digital image correlation, where we are doing the cyclic indentation test. You can see that this goes to the red highest strain, and then we are unloading it, so it comes back to the green and bluish tinge here. And once again, we are going to increase the strain, so that to check that it is coming back to the almost the initial position, almost more than 90% of recoverability is what that we have figured this out. So although we have started with the same alloy, system, we can see, like the same powder, we can see that just by varying the laser energy densities for the operations, we end up having different microstructure, different phases, and of course different properties, mechanical properties, and particularly pseudoelastic properties. So in especially for the case of aerospace application, additive manufacturing is often used for making these complicated shapes and all. And nickel titanium being very expensive and all, we want to reduce the material wastage, and additive manufacturing acts very promising for that. But as we can understand that we need to use the optimized parameters of additive manufacturing to get the best combination of mechanical properties. Okay, so with this, let us conclude the presentation here. I'd like to acknowledge, of course, my group of students who has helped me with all the kind of experimental works, and my collaborators from all across the globe who has helped me establishing this. And I'd be very happy to answer your questions.
Thank you very much, ma'am, for the wonderful session. So I may now request the participants to raise the questions. Either you can unmute your mic and you can directly talk to the professor, or else you can drop the questions in the chat box. So I'll read it out for you. Already we have a series of questions, madam, from Mr. Natraj MB.
Let me go to the chat box.
If you want, I can read it out, ma'am.
Yeah.
What is the indication of triple junctions in TEM studies?
Okay, just a minute. What is the question? What is the indication of triple junctions in TEM studies? Triple junction here, what I showed. Okay, let me share my screen once again. That is actually represents the grain boundary triple point. Here also, so this one you mean, right? Yeah, so this signifies the grain boundary junction. Okay, this is a separate austenite grain, this one is another one, and this one is another one. And this is just the triple point. It does not have any significance as such. So this is, you can see that this part here has been enlarged in the TM. Okay. Okay. How HCP crystal plane converts to FCC in XRD? HCP is not converting to FCC in XRD. XRD is a measure by which we can able to find out the crystal structure of any material. Nothing converts in XRD. Okay, and in this case, for the case of nickel titanium, it is a cubic structure that converts to monoclinic. There is no HCP or FCC here. Nataraj MV. Okay, I am not getting any response from Nataraj MV, so I'm not sure whether.
Mr. Nataraj MV, you may unmute your mic.
Yes.
If you want to. Yeah.
Hello, is it audible?
Yeah.
Yeah,
Yes.
ma'am. Yeah, thank you, ma'am. Thank you for the answer. And then, in general, NM is a HCP crystal structure. So, it to be a four-plane it is. So, nickel is the austenite FCC crystal structure. So, my question is like, if it is a HCP crystal structure, so how it can be transformed that four-plane to three-plane? Is there any conversion in XRDs? Hello.
Iridium has a separate crystal structure compared to individual nickel and titanium.
Okay. Okay.
Okay. Okay. I see the rest of the questions are mostly from you. So if you can please go ahead with the question. Due to the aging, precipitate is a good agreement, but is strain-induced precipitate possible in SMA? Strain-induced precipitate, no. Strain-induced phase transformation can form, but strain cannot form precipitate as such. Due to the formation of precipitate, there could be some strain, but strain is not supposed to form a precipitate.
Okay.
For precipitate formation, you need to have a compositional disbalance. You need to do something with the heat treatment or so on.
Okay.
Okay, the combination of twinning and martensite have known concept, precipitate and martensite combination. Precipitate and martensite combination, I'm not getting your question, Mr. Natraj.
Both are there in the as you have shown in the slides, ma'am.
Yeah,
So,
both are the different phases. Twinning
yes,
and martensite are not two different phases. Twinning is, martensite is in a twinned condition.
yeah.
So
Yes.
twinning, both the twins are martensite only. That is a single martensite phase, but precipitate is a separate phase. Phase is when it has a different crystal structure or different compound altogether, right? So the precipitate here is nickel Ni4 Ti3. So that's a separate compound with a completely different crystal structure than the martensite.
Yes, ma'am. Yes, ma'am. Even this martensite and twinning is especially so is related with striking fault energy also. So if no striking fault energy is there, then thing is possible. So here, especially nickel is I think 100 millijoule per meter square. I think the striking fault energy.
Again,
So
it is not about nickel. It is nickel titanium.
yes, ma'am.
So
When we combine with the nickel titanium, then so maybe the probability of martensite is due to the striking fault energy also.
this is not the mechanical twinning that we are getting. This twinning is happening because of the phase transformation. It forms in.
Okay.
Yeah.
Okay.
Okay. Martensite in general is brittle. Martensite is helpful to SMA. What you're talking about, martensite, maybe that is of steel that you're talking about.
Yeah.
Here, martensite is the terminology. Martensite is used, but the crystal structure and properties of the shape memory alloy martensite is completely different from that of steel. Why it is called martensite is because it undergoes a diffusionless transformation from austenite.
Yes.
That is why it is termed as martensite. As per the nomenclature, anything which is undergoing diffusionless transformation, we can term that as martensite. Okay. So it is not about helpful or anything. This is just the principle by which conversion of austenite to martensite is not the only factor of SMA. The main part is converting it back. So the reversible conversion. Okay, reversible transformation that makes shape memory alloy to recover its shape, which steel cannot.
Yeah.
Or iron-based system cannot. Okay, residual stresses in SMA during and after additive manufacturing. This is a very good question. Of course, there are residual stresses, and we also do study the effect of residual stresses. And these residual stresses are also, in most of the cases, they act detrimental, especially when we are talking about pseudoelastic recoverability. Okay, so these residual stresses can be harmful, and we need to either homogenize the component or the structure to get rid of these residual stresses. Again, residual stress will be good one if it is a compressive residual stresses, especially for the fracture fatigue kind of application. Compressive residual stress is a good news. But if we have tensile residual stress, we need to minimize that. Okay. Is there any possibility to calculate the volume fraction of precipitate? Suppose there is a related peak. Yes. Volume fraction is of course calculated from XRD itself. It has been calculated. So there is a paper which I have indicated in this
One
study?
small doubt,
Yeah.
even in addition to that, in the same question I mentioned, suppose for example, in general I'm talking, not to be particular to the nickel shaped only. So the precipitate peak is there in the XRD by doing some process. So like one to another two three peaks, if we take it as different process wise. So if the intensity is increased, does it mean precipitate volume fraction is increased?
Yes, to some extent, but then again, intensity of which of the peaks are more that, yes, of course, the volume fraction, that is how the volume fraction is calculated. But
Okay.
different process means what? Different heat treatment process.
Either heat treatment process or else surface modification technique by different process, different parameters.
Hmm. Okay, you can end up having different phases, different precipitates, and the different volume fraction. Certainly.
Yeah, ma'am.
Okay. So, can I go to the next question?
Yeah, yes, ma'am. Yes, ma'am. Please.
Will it possible to get strain-induced precipitate at sub-zero temperature in SMN? If again, uh, this, I mean, strain can give transformation, but not precipitate as such. For the precipitate, we need to undergo some kind of heat treatment. Is it possible to weld this alloys? Of course, of course. So this stents when it is used as a stent. All the different.
There is a one concept is like strain induced Martins that everyone knows. Even strain induced precipitate also is possible, like people are talking. Ma'am. So in that context, so I feel that in nickel based alloy, one paper is there with surface modification techniques. So they also mentioned very clearly, like by using strain as well as the temperature. Of course, they used a higher temperature,
Yes,
not to
that's
be
what
said.
I'm talking you. So you have to apply the temperature, otherwise it is difficult for the precipitates to form. That's the point.
Yeah.
Strain is an additional source of energy. When you are doing this with temperature, then only it can form the precipitate. Okay, so for making the precipitate, temperature has to be there. It is not like only just you are applying strain and the precipitates will form. That may
Suppose,
not be there.
suppose if the material is subjected to sub-zero temperature and I applied the strain, very high strain, not even like 10 power 2 or 10 power 3, 10 power 7 or like. So in that case, in a fraction of nanosecond kind of thing itself. So is it
That
possible
means
kind
impact. That is a kind of
impact?
impact. And
Yes, ma'am.
impact always comes with adiabatic heating.
Yeah, ma'am.
Okay, so there is this
Yeah.
internal heating that comes into the picture when you are increasing the strain at such a high rate.
Yes, yes.
This is a high strain rate deformation.
Yes, ma'am. Yes, ma'am.
Yeah.
So in that case, is it possible?
That could be. As I said, the temperature the material has to get the temperature. It does not understand whether you have placed it in a furnace or whether you have impacted with a very high strain rate.
Yes,
Okay,
ma'am.
when it gets the precipitate. Okay, regarding your welding question, this is how welding is done. So all these wires are being attached by welding, and that actually leads to this weld affected zone and some kind of defects due to welding, and that leads to like some of the properties, the shape recovery properties is being lost because of this welding. So of course welding is possible, but proper measures need to be taken.
Okay, and one more question I have not added here. So,
Okay.
will
Can I please
really
answer? Can I
yes?
please? I will request the permission of the chair to intrude here so that I can answer to others
Okay,
also.
okay, okay, okay.
Yes.
Thank you,
Okay, I
thank you,
can
ma'am.
see. Okay, you're welcome. I can see a message from Avinash Shelvarajan for thanking me. So thank you, Mr. Avilash, also. Uh,
Any any questions from the participants?
Someone has raised hand. So someone has raised hand. So please, Dr. Jai Ganesh.
Dr. Jay Ganesh, are you here?
Okay.
In that case, is there any question from the participants? You may either unmute your mic or you can post the message here. Sure.
Okay, if not, then I would like to ask Dr. Nataraj because he was asking something.
Thank you, ma'am. I'm not a doctorate, and then about to doctor, ma'am.
Okay, okay, okay. Then all the best.
Thank you, thank you. And suddenly I forgot, ma'am.
Okay.
Okay, in that case, can we conclude the session?
Thank you, ma'am.
Okay, you're welcome. Yeah,
Uh,
sure.
Thank you very much, ma'am. I'd like to convey my sincere thanks and gratitude for accepting the invitation and such a wonderful session. The session is really informative, and we hope that the participants all around the world here have gained knowledge and got benefited out of it. Thank you very much for accepting the invitation and being here, ma'am. It's our pleasure.
Thank you very much, Professor Tamil Vennan. Thank you, all the participants. Have a good day. Thank you.
Thank you. So, dear participants, thank you for being here. Hope you have had a wonderful session. And the feedback link is shared in the chat box. You may enter your feedback. And for the tomorrow session, we have another two different distinguished guests. And the details will be shared to you in the WhatsApp group, both the WhatsApp groups. You can join as per the schedule. Participants are requested to enter the feedback through the link shared in the chat box.